Welcome to The Explainer. Today, we're basically stepping through a portal into a mirror universe. Think about everything you already know about linear physics. Objects moving in straight lines, speeding up, slowing down, crashing into things. Now, I want you to imagine taking that entire world, that whole rulebook, and just spinning it. We are going to translate the physics of the straight line into the glowing, futuristic, circular mechanics of rigid bodies. Okay, let's dive into this. What exactly happens when our familiar linear world starts rotating around a fixed axis? Well, the real beauty of physics here is that we don't have to reinvent the wheel. And yeah, pun absolutely intended there. Instead, we just map our existing knowledge onto a completely new framework. Every single time an object rotates, whether we're talking about a child's spinning top, a merry-go-round, or a massive industrial turbine, it follows a set of rules that perfectly mirror the linear motion we already understand.
Here's our roadmap for today. First, the language of rotation. Second, spinning at constant rates. Third, bridging the linear and the angular. Fourth, inertia and kinetic energy. And finally, torque and rotational dynamics.
Let's kick things off with part 1, the language of rotation.
So think of this mapping as our Rosetta Stone. Instead of tracking a position along a straight x-axis like we're used to, we track angular position using the Greek letter theta, and this is measured relative to a fixed zero-angle reference line. Now, it's absolutely vital here to remember, we measure this in radians, not degrees. When that angular position changes over time, well, we get angular velocity, represented by a lowercase omega. It's the exact rotational counterpart to linear velocity. And when that spinning speeds up or slows down, we get angular acceleration, represented by alpha. We're literally just swapping out the letters, but the underlying concepts of tracking motion, they remain completely identical.
Now, you might be wondering, how on earth do we handle direction in a circle? In linear physics, you just move left or right, positive or negative along an axis. But in rotation, we use something called the right-hand rule. Just imagine curling the fingers of your right hand in the direction of the rotation. Your extended thumb literally points in the direction of the angular vector. But honestly, for your practical, everyday calculations, just remember this one simple, unbreakable rule. Clocks are negative. If a rigid body is rotating counterclockwise, its angular velocity is positive. If it spins clockwise, like the hands on a wall clock, it's negative. It's incredibly simple, yet totally crucial for keeping your calculations on track.
Moving right along to section 2, spinning at constant rates. This brilliantly illustrates that mirror universe analogy I was talking about earlier. Look at the left side here. These are our classic kinematic equations for constant linear acceleration. Now look at the right. They are exact replicas. Where you used to have linear velocity v, you now plug in angular velocity, omega. Where you had linear acceleration a, you just plug in angular acceleration, alpha. So, say a spinning amusement park ride, like the rotor, slows down at a constant rate. You don't need any new math to figure out how long it takes to stop. You just use the rotational version of the exact same equations you already know.
Up next is section 3, bridging linear and angular.
Now, what's really fascinating about this is how we break down what a point on a spinning object actually experiences in real life. Imagine you're a little bug sitting right on the edge of a spinning merry-go-round. Because you're rotating, you actually have two completely different types of linear acceleration happening to you at the exact same time. First, you've got tangential acceleration. This is you speeding up or slowing down along the outer edge of the circle, driven by the angular acceleration of the ride. But get this, even if the merry-go-round is spinning at a completely constant speed, you still experience the second type, radial or centripetal acceleration. Because you're constantly changing your direction just to stay in a circle, you are actually constantly accelerating inward, toward the center of the ride. These two components act perpendicularly to each other, forming your total linear acceleration.
All right, section 4, inertia and kinetic energy.
Whoa, take a look at this image. This isn't just a messy workshop. This is the aftermath of a catastrophic spin test explosion. In the industrial world, they test large machine components by spinning them up to massive speeds inside these heavy lead and steel containment shells. In this specific case, from our source material, a massive metal rotor was brought up to 14,000 revolutions per minute, and it completely shattered. The kinetic energy was so immense, it literally destroyed the heavy containment meant to hold it. That terrifying destruction was the result of a sudden release of exactly 2.1 times 10 to the 7th joules of energy. Calculating rotational kinetic energy isn't just some abstract math problem on a chalkboard. It measures a very real, very tangible release of physical force. To calculate that energy, we take 1/2 times the rotational inertia times the square of the angular speed. But wait, what exactly is rotational inertia?
Well, in our linear world, mass is just mass, right? It dictates how hard it is to get an object moving. But in our rotational mirror universe, we use rotational inertia, or the moment of inertia, represented by the letter I. Now, the total mass of the object still matters, absolutely. But what matters even more is exactly how that mass is distributed around your axis of rotation. The further the mass is pushed away from the axis, the significantly harder it becomes to start or stop the spinning. Think about it. If you grab a heavy pole right in the middle and twirl it like a baton, it's fairly easy. But if you try to spin that exact same pole by holding it at the very end, it's incredibly difficult. And that's because the mass is distributed much farther away from your axis of rotation. And that brings us to a brilliant mathematical shortcut called the parallel axis theorem. If you shift your axis of rotation away from the center of mass, you don't have to recalculate the inertia from scratch using a bunch of complex calculus. It's just a simple, step-by-step algorithm. Step 1, take the known rotational inertia going through the center of mass. Step 2, measure the physical distance you shifted the axis. We'll call it h. Step 3, just add the total mass times that distance squared. That's it. It mathematically proves that any shift away from the center of mass dramatically increases the rotational inertia of the object. Which brings us to our final part, Section 5, torque and rotational dynamics. Enter torque. So, the crucial point here is that torque is the exact rotational mirror to linear force. In a straight line, a push or a pull, a force, causes a mass to accelerate. But in our rotating world, a twisting action, torque, is a powerful vector that causes a rotational inertia to undergo angular acceleration. And because it's a vector, direction matters immensely. Net torque equals I times alpha. It is quite literally Newton's second law of motion, just translated perfectly into our glowing circular vocabulary. To get maximum torque, you always want to apply your force as far from the axis of rotation as possible and perfectly perpendicular to it. And once you're applying a torque, you are doing work. Just as pushing a box across a floor requires linear work, force times distance, twisting a wheel requires rotational work. You simply multiply the torque by the angular displacement, the change in theta. This work directly changes the rotational kinetic energy of the object. It's amazing. Every single dynamic concept you know perfectly reflects right back into the spinning world. So, we've completely mapped the linear world onto the rotational one. From angular velocity and acceleration all the way to the massive energies of rotational inertia and the twisting power of torque. I want to leave you with a final thought to take with you today. Now that you hold this translation key, look around you. Where do you see these invisible, glowing vectors in your everyday life? Is it the tires on your car? The hinges on your front door? The spinning drum of your washing machine? This mirror universe of rotational physics isn't just trapped in textbooks. It's spinning all around you every single second of the day. Keep analyzing, keep exploring, and I'll catch you on the next explainer.